All right, let's move on to Unit 7, gases. This is Chapter 5 in your textbook. We are going to skip over 5.1 and 5.2. I would maybe encourage that you do skim that over a little bit. It is going to give you a refresher on what pressure is. That's obviously important when talking gases. And it's also going to give you a refresher on like the three main gas laws that we've talked about before. You may be familiar with the names Gay-Lussac, Boyle, and Charles. And then the fourth law, which you may not have seen, Avogadro's law, is going to be another important one that we'll need for this chapter. So skimming those two sections may be helpful for you. All right. So let's just quickly go over a couple of things that we should remember, that we should understand when working with gases. First of all, gases are totally different than solids and liquids. They are very susceptible to changes in pressure and temperature. You know, we gotta really change the temperature a lot to take a solid into the liquid form, relatively speaking. And if we have a solid and we increase the pressure on that solid tremendously, it's probably not going to change very much. On the other hand, if we increase the pressure on a gas just a little bit, we'll actually decrease its volume, and that changes its properties. So we can do the same with temperature. We can increase the temperature of a gas, and that could increase the volume. So all of those things go into making gases very much different, very much unlike solids and liquids, and that's kind of why it gets its own chapter in this textbook. One thing with this chapter, there's going to be a lot of numbers. So you really need to plan and organize your work. So kind of get a flow, a system. I don't know what that's going to be. It might be different for everybody. In class, you might want to start with, okay, what am I looking for? So what's the question, my question mark? And then in the middle of the page, what knowns do I have? So what do I know? And then maybe on the right side of the page, you might, what equations do I want to work with? And again, this is totally up to you on how you want to do this. And then from there, you can maybe show your work below that. I find that finding some type of systematic way to solve these types of problems is usually beneficial. And then lastly, lots of numbers means lots of units. Please be sure to cancel and communicate your units effectively. One of the big concepts we're talking about in this chapter is pressure. Pressure in itself has a bunch of different ways that it can be communicated. The different units for pressure are atmosphere, millimeters mercury, torr, kilopascals. That's 4 different units for one single variable, pressure. So we need to be sure that we're in the correct units when we're doing our work. The biggest thing is, do your units cancel out to give you the correct unit you're looking for in your answer. Much of the math that you're going to do in this particular section can be done by rearranging the equation effectively so that units cancel out. After that, it's just plug the numbers in and go to work. Okay. So let's start out then by looking at this first equation. Hopefully we remember from the past that there's really 3 equations, Gay-Lussac, Charles, and Boyle, and all those equations, they relate pressure, volume, and temperature in some way. Pressure and volume are inversely related. As one goes up, the other goes down. Volume and temperature directly related. Pressure and temperature directly related. The good news about this all, there's a lot of stuff. You don't need to memorize all of those equations. In fact, if you can understand this equation on the bottom of the page here, you're going to be fine. This is called the combined gas law. This one right here. Just says the pressure, volume, and temperature of one state is equal to this arrangement of the pressure, volume, and temperature in a second state. Okay? And it kind of sounds like R2-D2, but no, it is not related to R2-D2. Brave little robot. Brave little drone. All right, so let's work with the ideal gas law a little bit here. Here's a sample problem that we might see. Let's say we've got a volume of gas, carbon dioxide. It's 121 milliliters of that gas. We have that gas at 27 degrees Celsius and 1.05 atmosphere. So that's a pressure. We want that gas to occupy a volume. We want it to actually increase in volume to 293 mils. And we want the pressure also to increase to 1.40 atmospheres. So we're saying, what does the temperature have to be in order for this gas to expand and also excrete this amount of pressure? Okay, so that's our question. Now, I don't want to give you the answer. There's the answer. But let's go ahead and look at the work. It's P1 V1 over T1, right? That is the equation we looked at on the previous slide. And all I'm going to do is make sure that we know which unknown is responsible for which number. Okay. So pressure 1, let's see, pressure 1. Well, our initial state is right here. That's pressure 1. That's this guy. Okay. All right, so we start at 1.05 atmospheres, so that's our initial pressure. How about our initial volume? That's this guy right here. I want to circle the unit too. That should happen all the time. Okay, so there we go. And then what about our temperature? Let's see if we can find our temperature for this particular instance. Here we go. It's 27 degrees Celsius right here. And that's T1 right here. All right, so let's venture over to the right side of the equation now. We're saying that if we've got a gas at these conditions and we want it to expand to a larger volume with a certain amount of pressure, what has to happen? Well, we have a new pressure at 1.40 atmospheres. That's P2 now. We also have a new volume, and that volume is going to be 293 mils. That's this guy right here. And so we have all of the numbers that we can plug in. Now let's look at our units. Do our units make sense? Will they cancel out? And I think they will. We have milliliters here and a milliliter, so we don't have to do anything with our volume. Atmospheres and atmospheres. Don't have to do anything with our pressures as far as canceling things out. And our temperature here is given in degrees Celsius, and our final answer needs to be in degrees Celsius. So it looks like we don't have to do any type of converting to get to the correct answer. So you should be able to plug all those numbers in. The way I would, I guess, do the math, I would solve all these things over here and just get one number. I'd probably multiply P and V over here and get one number. And then cross multiply and divide, and so that you get T2. And as you probably saw before, we're looking at about 696 degrees Celsius. That is our answer. There it is, 696 degrees Celsius. Okay. And now I want to talk about a specific condition that we're going to use a lot when it comes to gas laws. And this condition allows us to compare two different samples of gases using a reference condition. All right, so STP. Now, I know we think of the oil company STP. No, we're not talking about that. STP actually stands for Standard Temperature and Pressure, not Stone's Temple Pilots. No, Standard Temperature and Pressure. What that means, standard pressure is 1 atmosphere, or an equivalent to 1 atmosphere. So 101 kilopascal, 760 millimeters mercury. So standard pressure is 1 atmosphere. Standard temperature is 0 degrees Celsius, or what you'll probably work more with, 273 Kelvin. You got to really go way back in the Wayback Machine. Remember that these two are equal to each other, 0 degrees Celsius and 273 Kelvin. So if I had 7 degrees Celsius, how many Kelvin would that be? 280, yeah, good. Okay, so why do we use STP? It allows us to compare amounts of gases using a common reference. So instead of having to say, oh, at 1 atmosphere and 273 Kelvin all the time, we can just say at STP. Okay? Gives us a nice reference. All right. Now, that combined gas law, P1 V1 over T1 equals P2 V2 over T2. That's a lot of stuff. That's a huge law. But what you might have noticed in that particular gas law is that there seemed to be something missing. And that something that was missing is this guy right here. Right here. N. Remember what N stands for. N is moles. Okay. So the combined gas law had volume, it had temperature, and it had pressure, but it didn't have moles. So the combined gas law says nothing about the amount of particles in the particular sample. And that's a travesty, because that's important. We always talk about moles. Moles are incredibly important. They allow us to understand and figure out how much product is going to be made or how much reactant we're going to need for a particular reaction. My goodness, we need moles. So, is there a way that we can fit moles into the combined gas law in order to get a new gas law? that not only relates pressure, temperature, volume, but also moles. And there just happens to be. If you do some crazy math, which I did once in my life, but I haven't done since, and I'd like to do it again at some point, you can actually combine all three of these equations to get what we call, very ideally, the ideal gas law. And this is probably, if you memorize any equation in chemistry class, it'll probably be this one. Not because you have to, because that equation is actually given on the equation sheets for the AP test, but just because you're going to use it so much. Okay? It's actually commonly referred to as Pivnert. Okay, Pivnert, get it? Okay, Pivnert. And that is the combined gas law. Ah, very cool. And if we look at that particular, that's the ideal gas law. And if we look at this law, there's a lot of very common and visible things in there. We understand P is pressure, okay, and V is volume, and T is temperature, and N is moles. So we know all those things. But there's one new thing in there, and it's this guy right here. R, okay, capital R. All right, R stands for the ideal gas constant, or the universal gas constant. If you look above in these three equations right here, you'll notice that there's a K and an A and a B. Well, if you do a little bit of math with all of those things, and you come out, you'll figure out what's called the ideal gas constant. It's going to be interesting because we're going to actually do this in the lab. So R has a common value, and we call that value 0.08206 liter atmosphere per mole Kelvin. Ugh, what a unit. And it gives a lot of people headaches. So let me write it out. This unit, written out, actually looks like this. Liter times atmosphere over mole times Kelvin. Okay? You got to write that unit out because it's going to help when you cancel out things to try to find your final answer. Okay? Try to find your final unit. All right, so that's the ideal gas law. Let's do some work with that now. All right, an automobile tire at 23 degrees Celsius with an internal volume of 25 liters is filled with air to a total pressure of 3.18 atmospheres. Determine the number of moles of air in the tire. Okay, this is kind of a funny example. We never care about the number of moles of air in the tire, but it's still interesting to know. If you know the number of moles of air in the tire, you could figure out the number of grams of air in the tire, and then maybe that's useful. I'm not sure. So let's figure out how to do this. Again, there's the answer. We're looking at our equation. PV equals nRT. Okay, what are we looking for first? We're looking for moles. Okay, how do I know to use PV nRT? Why don't I use the combined gas law? Because of that, right? Combined gas law doesn't have moles. All right, so that's going to be my equation. Wait a minute, though. I don't like the equation like that. It looks ugly. It doesn't give me moles. So let's go ahead and solve for moles right away, right? Okay. There we go. And if we did that correctly, which I think we did, I'm fairly confident in my algebraic skills, we will find that that is our new equation. Now we just have to go to work, right? Now, one last thing. Do our units match up? Okay, well, let's see. If we remember R is the one that's going to determine our units, right? R is liter, atmospheres, mole, Kelvin. Okay, so that means my volume has to be in liters. Let's check that out. Yep, we got it. And that means my pressure has to be in atmospheres. Yep, we got it. And that means my temperature has to be in Kelvin. Oh, we have an issue. Right there. So we got to get 23 degrees Celsius into Kelvin. And that's plus 273, so it's going to be 296 Kelvin, right? All right, so if we plug that all in and we do all of our work, hopefully we can come up with the correct answer, which is 3.27 moles. Okay. All right. 3.27 moles. All right, so let's go ahead and do a little bit more application with the ideal gas law. Let's say we've got a 2.10 liter vessel that contains 4.65 grams of a gas at 1 atmosphere and 27 degrees Celsius. We want to know the molar mass of that gas. I'm wondering if we can do this. Well, let's think about this. We certainly can find the moles of that particular gas. We have enough information. And if you look down here, I went ahead and plugged all that in. Okay, that's all the information. And if I solve for n, which that will do, this is what I get. I get n right here. Okay. And remember, n equals mass divided by the molar mass. So what are we looking for? We're looking for the molar mass of the gas. So can we rearrange that? Sure. We can get the molar mass, capital M, equals grams divided by moles. Well, grams is given to you, as is moles. Well, we found moles, right? And there you go. And from that, we should come up with the correct answer. And that is going, well, I can't see units out here. I don't like the way that I did my transitions. Atmospheres, so there you go. There's your molar mass, 54.6 grams per mole. So you could ideally think, well, what if this was some unknown gas? Well, you'd probably be able to figure out a molar mass and then come to a conclusion as to what that gas might be. All right, let's talk about molar volume of gas. It's going to go a little bit long, but that's okay. You should be able to work this in class today. All right, for 1 mole of an ideal gas, it's 0 degrees Celsius. So if you have 1 mole of any gas at 0 degrees Celsius, the volume of that gas is 22.4 liters. And let's prove that. If you've got 1 mole right here, and here's R, and here's your temperature, right? And standard temperature and pressure, standard temperature, standard pressure, and if you do all that calculation, you're going to see that's 22.42 liters. That's for any gas. So if you have any gas at standard temperature and pressure, and you have got 1 mole of that gas, it's going to occupy 22.42 liters. Here's an example of how much that is. Here's a basketball. This is a men's basketball. And here's a flask that has 22.4 liters in it. So you see the relative size. That's about a mole of any gas at STP. I also have a cube in my room that will show in class. That's 22.4 liters. It's that size. Okay. And because Avogadro said equal volumes of gases have equal numbers of particles, this is true for any gas. Nitrogen, oxygen, carbon dioxide, carbon monoxide, nitrogen dioxide. Any gas at 22.4 liters is 1 mole. All right. And we call that number molar volume. All right, last problem here. So molar mass, we can kind of rearrange things, and with understanding molar mass, we can rearrange this equation to solve a little bit for density of gases. Okay, and I'll do this solving for tomorrow. I just want you to write down that equation, and then write the units that come along with it, and then we will show the derivation of this equation in class, and we'll do some work with it tomorrow. All right, that's 5.3 and 5.4.